Hello everyone. In this video, we will be learning how to use the steam tables. First, we must understand the state postulate. That is, the state of a simple compressible system is completely specified by two independent intensive properties. These properties can include specific volume V, pressure P, temperature T, and many more. Next, we need to understand quality. It is a useful ratio that will help us solve problems with substances that are a liquid-vapor mixture. It is only defined for substances that are a liquid-vapor mixture or are saturated, such as a saturated liquid or saturated vapor. Quality is equal to the mass of the vapor or gas in the system, mg, divided by the total mass, mt, where mt is the sum of the liquid mass, mf, and vapor mass, mg. We must also understand phase changes. There are 5 different cases that we should know about. The first one is the compressed liquid case. For a given temperature or pressure, when the specific volume, V, is less than the specific volume of a saturated liquid, Vf, it means we have a compressed liquid. Vf occurs for a constant pressure or temperature on the saturated liquid line, where the first bubbles begin to appear. So when V is less than Vf, we are in the compressed liquid region. The specific volume of compressed liquid is very close to the specific volume of saturated liquid. So for our purposes, we can assume that V for compressed liquid is approximately equal to Vf. Now let's consider a constant pressure P1. When the temperature T is less than the saturation temperature Tsat corresponding to P1, we have a compressed liquid. If we consider a constant temperature T1 and the pressure P is higher than the saturation pressure Psat corresponding to T1, then we have a compressed liquid. For a compressed liquid, the quality X is meaningless, since compressed liquid is not a liquid-vapor mixture, is not a saturated liquid, or a saturated vapor. The second, third, and fourth cases can be grouped together as saturated cases because of their similarities. They have some differences, which will be discussed as well. The second case is the saturated liquid case. This occurs for a constant pressure or temperature on the saturated liquid line, where the first bubbles appear. The third case is the saturated liquid-vapor mixture case, or saturated mixture case for short. This occurs for a constant pressure or temperature in the saturated mixture region, which is the region between the saturated liquid line and the saturated vapor line. The fourth case is the saturated vapor case. This occurs for a constant pressure or temperature on the saturated vapor line. The three cases occur in the transition between compressed liquid and superheated vapor. Let's look at some differences of the saturated cases. For a given temperature or pressure, when the specific volume V is equal to the specific volume of saturated liquid, Vf, then we have a saturated liquid. As mentioned before, Vf occurs on the saturated liquid line for a constant pressure or temperature. For a given temperature or pressure, when the specific volume V is larger than the specific volume of saturated liquid, Vf, but smaller than the specific volume of saturated vapor, Vg, then we have a saturated mixture, where Vg occurs on the saturated vapor line, where the first liquid droplets form, for a constant pressure or temperature. For a given pressure or temperature, when the specific volume V is equal to the specific volume of saturated vapor, Vg, then we have saturated vapor. The quality X is an important ratio to be aware of in the saturated mixture region. If we have a saturated liquid, the quality will be 0, since the mass of vapor is 0. If we have a saturated mixture, there is some vapor and some liquid, meaning a fraction of the total mass will be from the vapor, so the quality will be greater than 0, but less than 1. For a saturated vapor, all of the mass is from vapor, so the quality will be equal to 1. Now that we have gone through the differences for the saturated cases, let's look at the similarities. Let's consider a constant pressure P1. If the temperature T is equal to the saturation temperature Tsat corresponding to P1, then we can be in any one of the 3 saturation cases. Now let's consider a constant temperature T1. If the pressure P is equal to the saturation pressure Psat corresponding to T1, then we can be in any one of the 3 saturation cases. The fifth and final case is the superheated vapor case. An example is water that has completely boiled and no liquid remains. It is important to note that the superheated vapor is different from saturated vapor. For a given temperature or pressure, when the specific volume V is larger than the specific volume of saturated vapor, Vg, then we have a superheated vapor. As mentioned earlier, Vg occurs on the saturated vapor line, the point where the first liquid droplets form, for a constant pressure or temperature. Let's consider a constant pressure P1. If the temperature T is larger than the saturation temperature Tsat corresponding to P1, then we have a superheated vapor. Now let's consider a constant temperature T1. If the pressure P is smaller than the saturation pressure Psat corresponding to T1, then we have a superheated vapor. For a superheated vapor, quality is meaningless, since superheated vapor is not a liquid-vapor mixture, is not a saturated liquid, or a saturated vapor. Now that we understand the theory, here are some formulas that will help us solve problems involving substances that are a saturated mixture. In other words, involving substances with the quality X that is greater than 0 but less than 1. The first formula relates the specific volume of a saturated mixture to its quality. Specific volume V is equal to Vf plus X multiplied by Vg minus Vf. The second, third, and fourth formulas are the same formula, but instead of specific volume, they help calculate the specific internal energy U, specific enthalpy H, and specific entropy S, respectively. In the tables we use, Ug minus Uf is already calculated and included as UFG. Hg minus Hf is included as HFG, and Sg minus Sf is included as Sfg. Once we understand how to solve problems involving specific volume, we will be able to use a similar approach for specific internal energy, specific enthalpy, and specific entropy. These formulas are also listed in the formula sheet. Now, let's look at the tables themselves to understand how to read the values from them. There are three tables we use. The first one is table A4, the saturated water temperature table, which lists specific properties of saturated water for various temperature values. The second is table A5, the saturated water pressure table, which lists specific properties of saturated water for various values of pressure. The third is table A6, the superheated water table, which lists specific properties of superheated vapor at various combinations of temperature and pressure values. Let's look at table A4 first. The actual table is 2 pages and looks like this. But to make the explanation clearer, we will use this part of the table. Here is the part of the table we will use. The leftmost column contains various temperature values in the saturated mixture region. Saturation pressure for each temperature is listed in the second column and corresponds to the temperature in the same row. For example, a temperature of 20 degrees Celsius has a saturation pressure of 2.3392 kilopascals. Each row also contains the specific property values for saturated liquid and vapor, namely the specific volume, Vf and Vg, specific internal energy, Uf, Ug, Ufg, specific enthalpy, Hf, Hg, Hfg, and specific entropy, Sf, Sg, Sfg. If we are given the temperature and one more independent intensive property, for example specific volume V, we can go to table A4 and look across the row containing the given temperature. Then, based on the other intensive property, we can determine the state description. And if the substance is anything but a superheated vapor, we can use table A4 and determine all other intensive properties. If we have a superheated vapor, we will need to use table A6, the superheated water table. And then we will be able to determine all other intensive properties. Next, let's look at table A5. Table A5 is also 2 pages long and looks like this. To make the explanation clearer, we will use this part of the table. Here's the part of the table we will use. The leftmost column contains various pressure values in the saturated mixture region. Saturation temperature for each pressure is listed in the second column and corresponds to the pressure in the same row. For example, a pressure of 15 kilopascals has a saturation temperature of 53.97 degrees Celsius. Each row also contains the specific property values for saturated liquid and vapor, namely the specific volume Vf and Vg, specific internal energy Uf, Ug, Ufg, specific enthalpy Hf, Hg, Hfg, and specific entropy Sf, Sg, Sfg. If we are given the pressure and one more independent intensive property, for example specific volume, we can go to table A5 and look across the row containing the given pressure. Then, based on the other intensive property, we can determine the state description. And if the substance is anything but a superheated vapor, we can use table A5 and determine all other intensive properties. If we have a superheated vapor, we will need to use table A6, the superheated water table. And then we will be able to determine all other intensive properties. In the case where we are given the temperature and the pressure, we should go to the temperature table first. If that does not help, for example, if the temperature is higher than the highest temperature value in the temperature table, then go to the pressure table. Last is table A6, the superheated water table, which is 4 pages long. The first 2 pages look like this, and the last 2 pages look like this. Table A6 contains specific properties of superheated vapor for various combinations of pressure and temperature. As a general rule of thumb, we should always go to the temperature or pressure tables first to confirm that we have a superheated vapor. Then, we should head over to table A6. This helps save some time. Since the table is many pages long, we will use this portion of page 1 for the explanation. The part of the table looks like this when we have zoomed in. Right away, we notice that table A6 is structured differently than tables A4 and A5. It is organized into boxes for various pressure values. The saturation temperature, where applicable, is shown beside the pressure in parentheses. The leftmost column contains temperature values. This creates a large number of temperature and pressure combinations for which specific properties are listed. Each row in a box corresponds to the temperature in the leftmost column and lists the specific properties of water at the corresponding temperature and pressure. For example, at a pressure of 100 kilopascals, which is equal to 0.1 megapascals, we would go to this box first, and then read across the row with the temperature value, let's say 300 degrees Celsius. The intersection of the box and the row, shown here, contain the specific properties for water at 100 kilopascals and 300 degrees Celsius. These are the specific volume, specific internal energy, specific enthalpy, and specific entropy. With the knowledge we now have, let's try some example questions. Example 1. Find the specific volume, quality, and state description of water that is at 30 degrees Celsius and 200 kilopascals. Please pause the video and try the example first, then continue watching for the solution. Okay, here is the solution. Since we are given both the temperature and the pressure, we want to go to the temperature table first. In the first column, we locate the given temperature value of 30 degrees Celsius and look across the row containing that value. We can see that the saturation pressure at this temperature is 4.2469 kilopascals, and the given pressure of 200 kilopascals is higher than the saturation pressure. Therefore, we have a compressed liquid. Compressed liquid is our state description. Since we have a compressed liquid, the quality is not applicable. In the compressed liquid part of the video, we said that for our purposes, we assume the specific volume V of a compressed liquid to be approximately equal to Vf. To find Vf, we go back to the temperature table and look across the row containing 30 degrees Celsius. We look under the column of saturated liquid for specific volume and find that Vf is equal to 0.001004 meters cubed per kilogram for 30 degrees Celsius. We have now found everything that this example requires, and our answers are listed here. The final answers are in a box. Example 2. Find the pressure, quality, and state description of water that is at 130 degrees Celsius and a specific volume of 0.1 meters cubed per kilogram. As before, pause the video to try the example first, then continue watching for the solution. Alright, here is the solution. Since we are given the temperature and specific volume, we should go to the temperature table to find the state description. We will need to zoom in on this portion of the table, because it contains the given temperature in the first column. The portion of the table looks like this. We need to look across the row with the given temperature. We notice that the given specific volume, V, of 0.1 meters cubed per kilogram is higher than Vf, but lower than Vg. This means that our state description is a saturated mixture. Also, this implies that the pressure is equal to the saturation pressure corresponding to 130 degrees Celsius. We go back to the temperature table and look across the row containing the given temperature. And notice that the corresponding saturation pressure is equal to 270.28 kilopascals. Now we have found two of the answers for example 2. All we need now is quality X. For that, we will need to manipulate this formula. For X, we already know V, we just need to get Vg and Vf. To find Vg and Vf, we go back to the temperature table and look across the row with the given temperature. Vf is under the Vf column and is equal to 0.001070 meters cubed per kilogram. Vg is under the Vg column and is equal to 0.66808 meters cubed per kilogram. Entering these values into our derived formula, we find that the quality X is equal to 0.148. We have now completed this example, and the final answers are in a box. Example 3. Find the specific volume, quality, and state description of water at 200 degrees Celsius and 1000 kilopascals. Don't forget to try the example first before looking at the solution. Alright, here is the solution. We are given the temperature and the pressure, so we should go to the temperature table first to find the state description. We will need to zoom in on this portion of the temperature table, because it contains the given temperature in the first column. The portion of the table looks like this. We first look across the row containing the given temperature. Since the other given property is pressure, we look under the saturation pressure column and find that the given pressure of 1000 kilopascals is lower than the saturation pressure corresponding to 200 degrees Celsius. This means that our state description is superheated vapor. Since we have a superheated vapor, quality is not applicable. All we need to find now is the specific volume. For that, we will need to go to the superheated water table. The box corresponding to our pressure value of 1000 kilopascals, which is equal to 1 megapascal, is on the second page of the table, right here. Let's zoom in to get a better view. First, we choose which box we need. It's this one since it corresponds to the given pressure value of 1 megapascal. Next, we can use the given temperature value of 200 degrees Celsius to determine that we need to look in this row. We need the specific volume for this pressure and temperature combination, so we look under the specific volume column. The intersection of the temperature row and the specific volume column tells us that our specific volume is equal to 0.20602 meters cubed per kilogram. Now we have found all the answers for this example, and they are listed here. The final answers are in a box. Example 4. Find the temperature, quality, and state description of water at 500 kilopascals and a specific volume of 0.52256 meters cubed per kilogram. This example requires the use of linear interpolation, so only try it if you know how to use linear interpolation. Otherwise, continue watching to learn how to use linear interpolation and the solution to this example. Alright, here is the solution. In this example, we are given the pressure and specific volume, so we should head over to the pressure table to find the state description. The given pressure is in this portion of the table. So let's zoom in for a better view. We look across the row containing the given pressure of 500 kilopascals and notice that the given specific volume V of 0.52256 meters cubed per kilogram is higher than Vg for the given pressure. This means that we have a state description of superheated vapor. Since we have a superheated vapor, the quality is not applicable. Now, we only need to find the temperature, so we head over to the superheated water table. The given pressure of 500 kilopascals, which is equal to 0.5 megapascals, is represented by this box. Let's zoom in for a better view. We can start by writing down the information that we have. Pressure P is equal to 0.5 megapascals, and specific volume V is equal to 0.52256 meters cubed per kilogram. Each temperature in this box corresponds to a value of specific volume, and as the temperature increases, so does the specific volume, as we can see here. If we were to guess the temperature using the value of specific volume, we can start by figuring out a range the temperature must be in. The given specific volume falls in between these two specific volume values. This means that our temperature must be somewhere between 250 and 300 degrees Celsius. To get a better approximation for the temperature, we can use what's called linear interpolation. We can use this graph for a better understanding of linear interpolation. We have 3 points here. Point 1 with x value x1, y value y1. Point 2 with x value x2, y value y2. And point M, which is a point in the middle of point 1 and 2, with x value xm and y value ym. Let's say we know the x and y values for both points 1 and 2, and we want to find the y value of point M for a given x value xm. We can use the similarity of triangles to come up with a relationship. The similarity of triangles can be remembered in an easy way. Small vertical length divided by big vertical length is equal to small horizontal length divided by big horizontal length. Now we have a relationship with our known values and our unknown value of ym. When we isolate for ym, we get this formula. The formula sheet has the exact same formula, except the middle point is represented by an x and a y without the m. They look slightly different, but they mean the exact same thing. We are back at example 4 again, and now we will use the linear interpolation formula to find the unknown temperature. We can organize our known values and unknown values into a small table for easy reference. We have point 1 with a temperature of 250 degrees Celsius and its corresponding specific volume value. We will denote these as T1 and V1. Next, we have the middle point with the unknown temperature and its specific volume. We will denote these as T and V. Lastly, we have point 2 with a temperature of 300 degrees Celsius and its corresponding specific volume value. We will denote these as T2 and V2. The interpolation formula has x's and y's, which we can easily replace with our desired variables. Let's replace all the x's with v's and all the y's with t's. Now our formula will look like this. We simply need to plug in the known values and find that the unknown temperature is equal to 299.95 degrees Celsius. This falls within 250 and 300 degrees Celsius as we predicted. Linear interpolation is a powerful tool to get estimates for unknown values of middle points, but it should be used carefully since it assumes that the two variables are linearly related. In this example, the temperature difference between the two known points was only 50 degrees, so we can assume that the relationship between specific volume and temperature is approximately linear. But as the difference between the known points grows larger, the approximation becomes less reasonable. Here are the final answers for example 4, placed neatly in a box. We have now reached the end of the video. Thank you for watching.